All right. Um, so today, I'm going to teach you guys how to determine if a vector is in the span of a set of other vectors. So for example, we have our vector u, which is equal to 1, 2, -2, and v, which has components 2, 3, 7, and finally w, which has components -5, -6, and -40. And we're asking, is w an element of the span of the vectors u and v? So before we start with this problem, we need to first, I think, remember what span is. And all span is just the set of all linear combinations of some vectors v sub 1, v sub 2 through v sub n. So in this case, we want to generalize the span of u and v as sort of like a function in a sense. So what we're gonna do is we're gonna say, okay, let me try to find somewhere comfortable here. We'll say let x1, x2 belong to the set of all real numbers, then is there a solution to x sub 1 times the u vector plus x sub 2 times the v vector is equal to w. So this is a linear combination here. We have our u vector, our u, v, and w vectors, and we have our two variables that we need to find solutions for to make this equation true. So what we're going to do is we're going to expand this. So we know that this is equal to x sub 1 times 1, 2, -4 plus x sub 2 times 2, 3, 7 is equal to -5, -6, -40. We're going to factor these guys in. So it should be x sub 1, 2x sub 1, -4x sub 1. And I think I'm going to grab a different pen. I'll be right back. Okay. So we distribute this x sub 1 into our u vector. Then we do the same for v. So this is 2x sub 2. Oh, this is such a good pen compared to the other one. 7x sub 2 is equal to -5, -6, -40. So, if you haven't noticed by now, we pretty much just made a system of linear equations. So, we're going to say this moves to a linear system. We have x sub 1 plus x sub 2 is equal to -5. 2x sub 1 plus 3x sub 2 is equal to -6. -4x sub 1 plus 7x2 is equal to -40. And here's our linear system. So now what we're going to do is move this into an augmented matrix. And for those who I know I did a lot of work I didn't need to, but it's kind of nice to show you guys the process from getting here all the way down to here conceptually. So we're going to say AM, and our augmented matrix is going to be 1, 2, -5, 2, 3, -6, -4, 7, -40. That is our matrix. So now we're going to do some row operations, and we're going to get this down to reduced, or to just echelon form. So, let's see here. We'll say r sub 2 goes to r sub 2 minus 2r sub 1. This part's going to be pretty tedious, as all row operations tend to be. So that should be 0. 3 minus 4 is -1. Negative 6 plus 10 is 4. Almost messed that up. So that's our first operation. Then next we'll say R3 goes to R3 plus 4R1. 1, 2, negative 5, 0, negative 1, 4. So negative 4 plus 4 is 0. 7 plus 8 is 15. Negative 40 minus 20 is negative 60. All right, and now we're going to want to say row 3 goes to row 3 plus 15, row 2, 1, 2, negative 5. Should be 0, 0, and then 4 times 15, so this is also 0. So we ended up with a row of all zeros. Just so you know, that doesn't particularly mean anything, and this system is in fact still consistent because 0 is equal to 0. That's a true statement. So if you ever see a row of zeros, don't worry about that. That's perfectly okay. But this is in row echelon form now. And as we can see, in our pivot column here, we have, we don't have any columns that are non-pivot columns, basically. So we can tell that there is only going to be one solution to this linear system. So let's find those solutions by getting this down to reduced row echelon form. So we'll say R sub 1, I think we only need to do one more step, goes to R sub 1 plus 2 R sub 2. We'll just do this. All right, that becomes 1, 0, negative 5 plus 8 is 3. And then we have 0, negative 1, 4, 0, 0, 0. We'll do one last thing. We're going to say R sub 2 goes to negative R sub 2, 1, 0, 3, 0, 1, negative 4, 0, 0, 0. And if we rewrite this back as a linear system, we have x sub 1 is equal to 3, and x sub 2 is equal to negative 4. So, because this system is consistent, we know that there are solutions, and our solutions are right here. So, what we could say is our solution vector is equal to 3, negative 4. So if we wanted to write this out in the form ax is equal to b, we can say, where's our two vectors? We'll do this. We'll say 1, 2, negative 4, 2, 3, 7, where this is u, this is v, times 3, negative 4 is equal to negative 5, negative 6, negative 40. Not sure why I included this here, but that's another way to look at it, I guess. And that's it. That's how you find out if a vector's in the span of some set of other vectors. Have a good one.